Hello class, in this video we are going to work on problem 29.70 from the book, and in this problem the question we ask is what is the potential at this point P, at this point on the bisected line, due to this line of charge, to this object of length L. So this is a linear problem, a linear object, and therefore we need a linear density of charge, so that let's define lambda, the linear density of charge, as Q divided by L. So now to solve this problem, we need to break this object in little pieces, and little pieces like this one here, this blue piece. And this blue piece would have a width delta L, delta X, this width here, that is delta X, and it'll be located at a distance X from 0, right? So the amount of charge in this little piece here, delta Q I, would be equal to what? Would be equal to lambda times delta X. So what we are going to do is find the potential due to this little piece, and then find the potential due to each one of those little pieces along the line and add them all. So basically the potential due to that little piece, delta Vi, is equal to what? To 1 over 4 pi epsilon naught. Then you have the charge on that little piece, delta Qi, divided by Ri. What is this Ri? Well, that is the distance from this element to the point here, Ri. And if this coordinate here is Z, right, coordinate Z, then this Ri is equal to the square root of x squared plus z squared. So then we can rewrite this as 1 over 4 pi epsilon naught lambda delta x divided by the square root of x squared plus z squared. Okay, so now what we need to do is add all the contributions. So the total potential V is equal to the sum over all the little pieces that are going to exist on this object of the potential due to those little pieces, and that is 4 pi epsilon naught lambda delta x divided by the square root of x squared plus z squared. Okay, so this is uh, so far so good. So now what we do is we take the limit. So we say v is going to be equal to the integral from minus L over 2 to L over 2, right, of 1 over 4 pi epsilon naught, then lambda delta dx, right? My delta x here goes to a dx when you take the limit, and then the square root of x squared plus z squared. Okay, so that is your integral that you have to solve, and all this here, all this quantity inside the integral is a constant, so it comes out, so this can be written as lambda, which is q over L, right, over 4 pi epsilon naught L, and then you're going to have the integral from minus L over 2 to L over 2 of what? Of dx divided by the square root of x squared plus 6 squared. So in the appendix, in Appendix A in your book, we have that the integral of dx square root of x squared plus minus a squared, right? That is equal to the logarithm of x plus the square root of x squared plus minus a squared. Okay, so that is what is in your book. So we can use this result here. So that means that then v is equal to what? To q over 4 pi epsilon naught L, And then this is going to be what? This is going to be the logarithm of the square root of x squared plus z squared plus x, right? And all this between minus L over 2 and L over 2. So now we can evaluate this and we get that V is equal to Q divided by 4 pi epsilon naught L, and then we get ln of what? The square root of c squared plus L over 2 squared plus L over 2 divided by the square root of c squared my plus, sorry, L over 2 squared, and here is a minus. That's a minus. And that is your solution. This result here, that is the solution to the potential, the line of charge. That is the potential at this point due to this line of charge here. Okay, thank you.